So to summarize what we want in a test statistic, what we're saying is if we have bigger differences in sample means, or if we have smaller variances within groups, in both of those cases, we want to create a test where we're more likely to reject the null hypothesis of equal population means. So we want a test statistic that reflects both how different the sample means are from each other and also how big the variances are within groups. And we want to reject the null more often when the differences in sample means is big and also when the variances are small within groups. So the way we're going to talk about this test statistic is by starting with a really simple data example. And although I said that the motivation for this whole discussion is that you might sometimes have more than two groups that you're comparing, I'm actually going to do it for just two groups because it's easier, and I think you'll see how it generalizes. This is our little example data set. It's very small. So I want to reuse A and B because those are some nice letters. They no longer refer to those three pictures. Now they're referred to two groups. Okay. So in group A, I have 3 data points. Suppose my data points are 8, 10, and 18. So you can imagine something like I'm comparing first years and sophomores. I'm calling those A and B, and here's the number of extracurriculars people are involved in. I hope that nobody's involved in 18 extracurriculars. That is pushing it. So is 8, and so is 10, and so is 6, but here we go. So in group A, the 3 data points are 8, 10, and 18. In group B, the 3 data points are 2, 4, and 6. So we can immediately calculate some things. I'm going to use general notation here instead of bars and variable names. I'm just going to write mean of A because I think it'll help us keep our bearings. So the mean of the 3 values in the first group is 12. The mean of the 3 values in the second group is 4. And the overall mean of the 6 values is 8. Okay. And we're going to consider a couple possible models. The first model that we're going to consider is called the equal means model. It's going to be exactly what it sounds like. But I also want to stop here and give it another name. Now, there's going to be a lot of this in this lecture. Every quantity I mentioned has like 2 billion different names, and I'm going to tell you what they are. Why? Because part of the point of this course is to pull together people who've had their interest sets course in different fields, to pull together people who are studying different majors that involve statistics, and let you know that we're all talking about the same quantities. We might just be calling them the same different things, right? So something that you've learned to call a certain term, right, actually means the same thing as these other terms. Also, as you go forward, as a data scientist or statistician, perhaps, I want you to be the person in the room who says, hey, this is just another name for blah, blah, blah. It's actually part of the learning to realize that the quantities and ideas we're talking about go by lots of different names. So let's start doing that. The equal means model is also called the reduced model. Why reduced? Well, you can't have a simpler model than assuming that the means are the same in every group. So what I'm going to do to talk about this equal means model is I'm going to write down our 6 data points. I'm just going to write them down. 8, 10, 18, 2, 4, and 6. The equal means model says that the A group and the B group actually have the same population mean. It's like saying the null hypothesis is true. In the equal means model, the 2 groups have the same population mean. So if you want to make a prediction of the value for any particular data point, you don't have to consider whether they're in group A. You should just use as your prediction the overall mean that you've observed so far. So again, if a new student walks into the room and we're trying to predict how many extracurriculars she does, we would just give back the 8, which is the overall mean here, without regard to whether she is a first year or a sophomore. Okay, so now what I'm going to do is I'm going to write down the difference between each data point and that prediction. Remember that these are called residuals. This is a familiar idea, I think, now, right? I'm going to calculate the residual for each data point under the equal means model. Okay? So these are all residuals. So now I have a bunch of residuals, right? Let's put parentheses around them. And what have I been doing with residuals in this class? I want to summarize them, so I'm going to square them and I'm going to add them up. Why am I squaring them? Because if I don't, it just adds to 0, just like with variance, because it turns out this is very much related to variance. I'm going to square them and I'm going to sum them up. And what the resultant quantity is going to do is give me a sense of how well the equal means model fits. If the equal means model fits great, then all these differences should be pretty small. If the equal means model fits terribly, then these should be pretty big values. Now, what do we mean by big and small? Well, it's all relative, so we're going to have to compare this quantity to some other quantities. So if we actually do this calculation here, which of course is possible, we get a number. So this is equal to 160, okay? And let's say it in words. So this idea reflects how far the data points are from the overall mean, which is my prediction for each of those data points under the equal means model. Now, let's give this quantity some names. So 160 is what? Well, I'll usually call it the sum of squares total. Why? Well, it's clearly a sum. What is it the sum of? Well, a bunch of squared quantities. Why total? Because I'm using the equal means model, I'm using the reduced model. This quantity represents all of the variance in the data set, because I'm saying how far does every data point, how much does every data point deviate from the overall mean? So this is the total amount of variation in the data set across all the data points. I'm not excluding any data points. I'm not focusing on any one particular group. I'm just saying, give me the entire data set. How much does each data point vary from the mean of all the data points? That's the sum of squares total. We often call that SST, but guess what? It can also be called TSS for total sum of squares. In addition, we could call it sum of square residuals, comma, reduced, because it's the reduced model. Sum of squared residuals, comma, reduced. And if we wanted to abbreviate that, we could awkwardly call it SSR with a little reduced down there. Okay, so is that awkward that it has so many names? Yep, but part of the learning is to start to be able to recognize those. Crucially, this quantity relates to a quantity that you already know about. So when else have we taken a bunch of data points, seen how far they are from the overall mean, squared them, and added them up?